All right, so I'm going to give you the punchline straight away, which is essentially that in 40 years or more, I'm actually, 40 is a bit generous, it's considerably more than that now, as you can probably tell by looking at me. I've never really seen anything like what's going on in academia right now. I think it's profoundly different and beginning to be that way. And it's really the response, as we all know and you're all involved with the digital transformation of society. And it's touching every discipline. That's the difference, I think. So we're doing projects with religious studies. We're doing projects with economics. We're doing projects in biomedicine. We're doing projects in fintech, all of them driven by, obviously, a lot of data. So I think that leads to thinking about all of this in a certain way. And so, and I'll get to that in a second, because it's really my own bias, and I'll explain it in terms of my bias. But clearly what's going on is disruptive, and I believe that higher ed, including what we're trying to do, and I tell our president this all the time, and I'm telling your president, that we better pay attention to this. And I can see that you are already, so I think that's really positive. It's gone on since the early 90s, but basically it's now really the driver, in my opinion, for healthcare of the future. So, and that's all come from digital data. So we've seen this essentially exponential change. If you translate that into what's happened in the life sciences as one field, so I'm saying all this not because I want to emphasize the life sciences, but just to emphasize what I feel is happening in other fields as well. If you're a historian, your life is completely different going forward. You know, when I started in this business as a computational biologist, there was just a handful of us, and we were like complete outsiders. And then the Genome Project, as we said, changed that. But as it emerged, I think what happened is industry got onto it. And industry thought this was going to be the change that was going to change everything. The issue was the time frame. So half of all the bioinformaticians, half of the people doing this kind of work, computational biology, went into industry from academia. Within 5 years, when it didn't bear the fruit that industry expected, many of them came back and into academia, because the time frame wasn't quite right. At that point, a lot of this became a service. It wasn't recognized as being academically a real discipline. It was a kind of a service in the field. Then what happened as it became more and more prevalent and more important to the future of the life sciences and the future of healthcare, it really became a partner. And then what I said at this meeting, I've changed the slide because I said it was going to happen in 2020. It's already 2022 and it's still not really there. But it's the notion that healthcare is going to be driven by computation, not driven by experiment and so on. And I think there's just, in my mind, there's no question that that's already starting to happen. So the question I ask myself in all of this is, given this history, if we've had this change in one field, can it happen in other places? And I'll give you an example from a completely different area. When I was doing this role as Associate Vice Chancellor, I actually went over to talk, I was actually in the School of Pharmacy and Pharmaceutical Sciences. I went over to talk to someone in the business school, in the Rady Business School. And they had a paper on their desk. I looked at it. It was one of our papers. And I said, "Oh, you knew I was coming over and you pulled out one of our papers just to be nice." He said, "No, I don't even know who you are. I actually using a statistical method in this paper. We're analyzing marketing data." I said, "You're kidding, right?" And he said, "No." So we started talking about it. We then had a meeting. This is around 2012, 13. We then had a meeting that we organized between us. It was called Big Data at UCSD Day. More faculty came to that meeting than any other meeting in the university's history, partly because they smelt money. Big data was the whole thing. So if you're not familiar with this, that every year Science magazine publishes the breakthrough of the year. This past year, it was effectively the solution to protein structure prediction. If you take a protein that we're obviously composed of, there are 20 amino acids, and a typical protein is 300 amino acids, let's say. That's 20 to the 300 possibilities. That's more than all of the atoms in the universe. Right? What we know currently are of the order of, say, 10 million protein sequences. So this is so you can imagine a string of beads, 20 different colored beads, that's the protein. There's 10 million or so of those sequences. They fold up into the order of thousands of different shapes, and it's those shapes that infer biological function as well as disease. Every 2 years, a group of people who are doing these kinds of predictions would get together, and they would get hold of experimental sequences, the linear strings, knowing that the 3D structures have been solved experimentally but weren't yet available. They would make their predictions, and then they'd all get together and compare their results to each other. We participated in this early on. We were pretty useless, I have to say. But it created a series of benchmarks for what progress in the field over that period of time. Over the years, with these competitions, you can see over the years, and the y-axis is essentially the correctness of the structures. And you can see that there was this massive jump with this so-called AlphaFold 2 on the left-hand side here in 2020. What's so profound about it is that it's almost as good as the experimental structure. So this, as it stands right now, one of these computations can be done in literally minutes to hours, whereas an experiment to get to the same result would take months, or could take months. So this has a profound effect on biology, and it's not just the simplicity or simple structures. You can see on the right-hand side that even the most difficult cases get solved fairly easily. The translational possibilities that come out of this one breakthrough are absolutely astronomical. So effectively, they've now got, of all of those millions and millions of sequences I meant, they've generated computational structures which are going to have downstream an enormous impact on healthcare and food production and energy production and biodegradation and so many other things. It's just amazing. It's all based on open data. Let's just speak about the importance of integration. And this is just an example I really like to illustrate this. So I'm sitting in my office one day and there's a knock on the door, and it's this fellow, Thomas Hartke. He comes in, he says, I'm a trauma surgeon and I work in the ER. I said, oh, what do you want? And he says, I want to learn about data science. I said, why do you want to learn about data science? He said, well, I've been doing trauma surgeries for a long time now. And when patients come in, and frequently it's from a car accident. And what I noticed is that, well, things happen. So they die in a scanner. On the other hand, if they recover and I'm talking to them and I learn the kind of accident they had, I started making these mental correlations between the kind of accident they had and the kind of internal injuries they had. He said, I got interested enough in this. I went and I actually learned some Python, and I started playing with R in my spare time. I said, you have spare time? He said, not much. And he said, but I got stuck. I need help. And I said, well, what have you done? He said, I went to the Department of Motor Vehicles, and I downloaded all the crash records for Virginia. I said, just working with a DMV, you deserve a medal already. And then he said, I've got access to the EHR. Anyway, he started a master's in data science and now has found the correlation, these correlations in a quantitative way, with the intent of the idea being that the emergency responders will send a picture of the crash to the ER, so when the patient arrives, they know what kind of crash it is, and they then look for use those correlates to actually look at internal injuries for particular types of internal injuries first, with the hope of actually narrowing the amount of time to treatment that would actually help the patient. So to me, this is like the epitome of what data science can do. It's basically the notion that who would have thought about bringing this really transport data and electronic health data together to actually come up with things that are going to have a positive effect on society. give you one example very quickly from our own recent work, is there was sort of anecdotal evidence that statins, which of course have positive effects on cancer. So that's obviously statins are prescribed for something else, but it was noted that different statins, if you drew a matrix, that different statins would have different potentially positive effects on different cancers. We then came up with what looked like some correlations. We tested those in animal models, and then you make predictions at the molecular level through biochemical pathways of what might be going on. So it's a multi-scale modeling that goes from molecules all the way to cohorts of patients to try and bring all that together in one understanding. We have an advisory board of people who are actually hiring our students. So they're really important to us. We have the CIO of Capital One, for example. We have a fellow called Scott Stephenson, who's just stepped down as the president and COO of Verisk Analytics, which is a Fortune 500 company. So these are hiring a lot of our graduates, and so we listen very closely to, the feedback loop needs to be made better, but that's what we're trying to do. And frankly, what they're telling us right now is we need data engineers much more than we need data scientists. And I can imagine that, I suppose. But yeah, and we haven't by no means solved how we're going to deal with this. But or at least we're talking and thinking about it. So I leave you with this. Have I overstated the case for data science? Looking at you, I'd say you probably think so. Are we currently doing the best by our students in the way we're teaching them? I'm sure there are other questions. Are the models we propose the right ones for what we're doing, at least going forward? And what should we be doing differently? And there's probably a lot. So with that, I'll stop. Thank you for your attention.
Thank you, Phil.